invited talk is by Swarat Chaudhuri. Swarat is a professor at Rice University. He got his PhD at University of Pennsylvania. He was then a faculty at Penn State. And he is well known in the areas of formal methods and algorithms for program analysis. And in recent years, he's also introduced concepts such as smooth interpretation, a way to view programs from a continuous perspective, and has been working on big code topics lately, a part of Muse project, among others. And so today he's going to tell us about a core topic of this talk. I'll let him explain it. So thanks for coming.
Thank you, Victor. Yeah, like a lot of folks in this room, I spent a lot of time thinking about program synthesis. And the statement of program synthesis, as understood in the CAV community and also related communities like programming languages and software engineering, is traditionally something like this. There is a formal specification, there is a programming language, and then your goal is to find a program that meets the specification. But what I'll talk about today is about some recent work, very recent work, which is challenging this traditional definition. We are seeing increasingly a convergence between program synthesis research and research on artificial intelligence and machine learning. And a lot of that is really about going from that assumption of a formal specification to broader classes of specifications. And that's something that I'm going to talk about today. But before I do that, it's worth recalling that the original work on program synthesis actually was in the world of AI. This was back in the day when AI folks were all excited about symbolic systems. And then more recently, the problem was picked up by the PL community. And many applications have been discovered. Microsoft Research did this excellent work on using program synthesis for discovering flash fill macros. There's work in optimization. There's work on application of these sorts of ideas in database optimization. There's a lot of different kinds of work. But that's not, of course, what I'm going to talk about here. I'll talk about how this line of work in programming languages is coming together with AI and ML research. And so here's just an example of this convergence that, just this year in ICLR 2018, one of the premier deep learning conferences, there were 14 papers on program synthesis. And there's actually a very nice blog post which you can go and look at if you're curious about what these papers did. So the themes that are coming out of this convergence are something like this. So first of all, statistical learning methods can really benefit program synthesis. And a second part of this is that there are very interesting questions in program synthesis for statistical learning. So it's not just enough to use standard issue statistical models. There's a lot of innovation that can happen, that needs to happen there in the world of machine learning for us to tackle program synthesis problems. And a third theme that I'll actually talk about today is that program synthesis, this combination of statistical and symbolic synthesis, can be used not just for traditional software engineering tasks, which is what folks in programming languages and formal methods have traditionally looked at, but also more mainstream AI applications. So for example, videos, speech and image perception, things like this. Okay. So now let's dive into this a little bit deeper. So let me start by summarizing what I believe are the two big challenges in synthesis at this time. So one big problem is specification. As I said earlier, the traditional view in programming languages has been that a specification needs to be formal. But really, how many applications in the real world are there for which you can write a full formal specification? Right, so now my friends in the deductive verification community would probably not be happy with this statement. And I'm very much a believer in formal methods, but I also think that formal methods are costly. And while certain safety critical applications really need full formal methods, that's not really practical for a lot of tasks in the real world. But at the same time, if you're not going to have a full formal specification, you could have all sorts of meaningless results. So, for example, even going back to the kinds of synthesis that have led to real-world success, synthesis from tests. So if your test set is something very incomplete, then it's very easy to satisfy that while giving completely meaningless results, right? So somebody tells you that on input X, produce output Y, on input X prime, produce output Y prime, you just write a big if then else that matches the specification trivially, right? So how do you avoid these sorts of meaningless results? And the second big problem is something that the CAV community actually has spent a huge amount of resources in tackling with some significant successes, but definitely not total success. And that's the problem of combinatorial explosion. So at the end of the day, when you're talking about program synthesis, you're talking about finding one or a small number of programs from a very, very, very large space of programs, right? And this space quickly blows up. And we in the programming languages, formal methods communities, we have spent a lot of time coming up with strategies to overcome this problem, and the use of language abstractions, the use of types, the use of nice data structures, constraint solving. But all of these ideas can only take us so far, right? And so there is this question: how do we go to the next level of scalability in synthesis? And my claim is that statistical learning can help with both of these problems in a fundamental way. And the first part of this is that if you have ambiguous and incomplete specifications, this is something folks in machine learning deal with all the time, right? So we are constantly looking at fuzzy data structure, fuzzy data types like images and speech signals and so on in machine learning, and statistics helps us interpret the uncertainty that is there in these kinds of fuzzy specifications. So we can perhaps apply such a thing in synthesis as well. And the second part of this, which I think is a very interesting question for learning, is that how do we learn to search a large discrete space of objects? So it turns out that there is some work in the machine learning community on this topic, where essentially the idea is that you get a lot of experience about how a certain search algorithm behaves, right? So what kinds of strategies are more likely to produce success? What kinds of strategies are more likely to produce failure in various contexts? And from all of this data, you create a model of what the algorithm should do. Now, of course, if you could come up with such an algorithm, such a model, then our search problem would be significantly solved, because if you think of it, the entire combinatorial explosion in these sorts of search problems comes from the fact that oftentimes, at intermediate states of the search, you have a lot of choices, right? If you had a model that could predict what is the right choice at this point, then the combinatorial explosion would be significantly contained.
So about that, right, if you can predict in a small fraction of cases, right, then if you narrow down the choice to 2, you have 2 to the n. If you narrow down choice to 1.5, you still have 1.5 to the n. So
yeah, but empirically, there's a significant difference between 1.5 to the power n and 2,000 to the power n.
Yeah,
it's a constant factor, but it's a significant factor. Okay, so rather than talking more philosophically like I have been until now, I'm going to talk about some concrete examples of these ideas. And specifically, I'm going to talk about 2 problems that we have looked at recently. And if I have time, I may go into a third. The first problem is actually, it's in the domain of software engineering, industrial software development. And so that's what I'll talk about first. And then after that, I'm going to talk about a problem which is more in mainstream AI, game playing, control, that kind of application. And we'll see how program synthesis from these sorts of ambiguous specifications are important in both of these settings. Okay, so the first problem is something like this. So you want to do program synthesis, but from very fuzzy specifications. So let's think of natural language, but actually this can be also extended to other kinds of inputs. So here is an example of an input for our synthesis system. So you have a method that you're trying to write, and the goal of this method is to read a bunch of lines from a file. So you have this empty method body, and inside that you write a comment that says, read some lines. And then what you want from the program synthesizer is a program that looks like this, and this is written in Java, of course, where you are basically figuring out how to read lines from a file. So you open a file reader object, possibly open a buffered reader object, and then you read the buffered reader line by line, and then at some point you close and you catch a couple of exceptions. So now you may say that how can I possibly get this from that, right? So the answer to that is that if this were the only thing that you were working with, then of course you couldn't figure out all of that information. But the thing is that when we are working with a programming language, there is a lot of context. There's a lot of other code that have been written historically using this language. And so from that, you can come up with a useful model of how to accomplish various sorts of things. So for example, you may know that, okay, whenever I see programs in the real world that read some lines, then they tend to use a buffered reader object, right? And then you don't tend to just read a single line, you tend to read a series of lines in a loop. So things like this. So there is this background knowledge that can be used to come up with this sort of idiomatic code. Now, one thing I would like to clarify over here is that what we see over here is not necessarily a complete program, because as you see over here, there is this catch block which contains nothing, right? So why does it not contain anything? Well, because you haven't really said anything about what needs to be done inside that catch block, right? So, and neither is it something that's universal information that you can learn from a code corpus, right? So the way to think of this, just to clarify, is that you're trying to accomplish some common API usage task, and you can think of this, if you want a concrete application, as a generation of examples, idiomatic examples of how to use the API, and then the expectation is fully that you're going to do something on top of this and fill out the rest of the code that needs to be written. Okay, so then this is the setup a little bit more abstractly. So we have a user who has in their mind an idealized program, and then they give a bunch of text. So we are going to think of this as a sequence of keywords that describes the intended program. And then there is also a context in which the synthesized code will go in, and that's abstracted by this type environment. Okay, and then the synthesizer is going to have to come up with some likely implementations that match these keywords and this type environment, and we also require it to be type safe, right? So there is a minimal correctness, a formal correctness bar that we need to be satisfied. Okay, so I'm just going to give you a demo of the system that we have called Bayou for this task. And you can actually go to this website, askbayou.com, to see some other examples. So here you can. I'm just going to give an example. I'm just going to write in natural language. There's also a more structured syntax. So let's say that I write, read some lines, and this is the same program that I showed you earlier. Oh, sorry. I deleted something more. And then what we are going to get from here are a series of programs. And this is going to be a probabilistic approach. So you're not going to get just one result, but you're going to get a set of results. And so here you see that you are opening a file reader, you're opening a buffer reader, you're reading in a loop, but you're also using this using a string builder over here for some reason, because I guess that co-occurs with these other things. So here you have just a read line program. This is exactly like the one that I showed you earlier, but this one just reads a single line. And then, here you have the program that we saw earlier where you are reading the buffered reader in a loop and so on and so forth, right? So basically it has learned these idioms from the corpus, and then somehow it's making sure that we are going to get these, type-safe compilable code snippets. Okay, so yeah, as I said, you can go to the website and play with it if you're interested. Yeah, so now I'm going to get a little bit more detailed. Just how do we formalize this problem? Well, it's something like this. So we are going to think of program synthesis not in this traditional way, where the goal is that you're given a formal spec and find some correctness some program that satisfies the formal spec. But instead, we are going to think of program synthesis as this probabilistic process. So you're given some input X, and your goal is to come up with a distribution over programs that is conditioned on this input X. And so the learning problem is something like this. So you are given a large set of programs. So we set it up as supervised learning. So you're given a large set of programs. These are programs that are taken from a corpus. And each program is annotated with some text. So where do we get this text? Well, if we had something like java.comments, that could be used for this purpose. But right now, we are just extracting some natural language from the program by taking the tokens and then chopping them up by camel case and so on. So we have a training set that looks like this. So from here, we just follow the usual supervised learning approach. So our goal is to find parameters for our model, right? So we have a parameterized distribution, so that's a statistical model. So we find optimal parameters that maximize the conditional likelihood. So basically, given X, you want to be able to predict the Y, the program that is actually there in the training set, right? We bias our training in this way. And then synthesis becomes very simple. So once you have learned this model, somebody has given you a specific X, and then your goal is to just run the model and come up with a likely program. So now one question over here is that in the recent past, there has been a lot of work on generative models, right? So there's a lot of work on automatic image generation, automatic generation of text, and so on and so forth. So could we use some of these statistical models for this purpose? And it turns out that the answer is no. And this is an example of why, for success in this domain of programming, ideas from statistical learning actually need to be combined with programming language ideas, right? So we need a synthesis, if you will, of the two lines of thought. And why is this so, right? Why are these generative models not good enough for this? Well, the reason is that programs are a very highly structured form of data. So there are, first of all, correctness constraints, like, say, type safety. So if you're asking a generative model, a standard issue generative model, to only generate type-safe programs, it's unlikely to succeed because small differences in the code can make a huge change to whether or not your type safety constraints or other kinds of constraints are satisfied. And then another problem is that the training data, code has a lot of junk in it. So there are a lot of low-level names, low-level, different ways of implementing the same construct. And so as a result, there is a lot of low-level noise in the training data that can confuse a learner. So this is something we empirically found, that direct learning over source code just doesn't seem to work as well. And so this is where we bring in the very natural PL insight of using abstractions. And so this is a carefully designed language of abstractions where we basically take programs and abstract them into this intermediate language where all of the local names from the program are erased and they're replaced by their types. And there is also some other stuff that happens. So for example, we take the many different ways of writing loops and unify them into, convert them into the same kind of syntax. So this is the kind of thing that results when you abstract a program on the program on the left-hand side. And so this is still a tree-structured object. So it's still an AST, but it's a more abstract AST, right, where all of the local names are gone. And so it turns out that this, because this abstraction is fixed, your learning problem can be cast now as, you want to find the optimal parameter so that, you produce the abstractions of the programs in the training set on the corresponding inputs. So then this is what the synthesis algorithm looks like. That we are going to have this model that now learns not over these programs, the complete source code, but over these what we call sketches, these abstractions of programs. And of course, then we have to do something about the fact that our end goal is to produce a program, not a sketch. Right? The programs that we get, they will have local variables and all sorts of other things. So how do we go from sketches to programs? Well, it turns out that this is something that we in the programming language community have been working on for the last 15 years. Programming by sketches or program synthesis, given a sketch of the desired program, this is a very well-studied problem. And we can use ideas from there. So then altogether, it looks like this. So you have a statistical model that goes and gives you some sample sketches that are going to fit the inputs that you are starting out with. So this natural language text or these keywords. Okay, and so these sketches are then, they're basically programs where you have, missing, for example, loop guards and missing arguments of methods, but they're types. Right? So now your problem then is that you're given the type of an expression, synthesize an expression, right, that matches that type. So this is something for which you can use this line of work called type-directed synthesis, and that's what we do, and that's how we got the programs that you saw on that web page. Yeah?
Both of these phases can produce multiple solutions. So if you have multiple results for type-directed synthesis, then how do you rank the whole thing in that list of things?
Yeah, so for this side, since we have, so for this part, when you are getting a bunch of sketches, you also get probabilities for each of those sketches. So this is something that's coming from the data. So you can imagine, and in fact, this is something we do, doing some maximum likelihood estimation to get the most likely result. But for the last part, where we are generating some programs from a sketch. So that part is heuristic because this is not driven by any information in the corpus.
So you just generate one that you think is good for a given.
Yeah, we generate a ranked list, and this is based on some cost metrics such as we want short programs and so on and so forth.
But so again, you have many choices, and I don't understand whether you restrict one of them to just one choice.
It's not one. I mean, it's going to be a ranked list, but it's going to be based on desirability according to some heuristic criteria.
And so you combine the probability here with the desirability here to a single rank. Okay.
Yeah, and that combination has to be heuristic, right? Because it depends on some heuristics over here. Okay, so I'm not going to go into the details of the model too much, but I'll just say that it has this encoder and this decoder, like you saw in several other talks in this workshop. And basically, what this encoder is that it's a neural network that takes in the input keywords, the text that the user has given, and then it converts it into this latent representation, which we call Z. And you can think of the Z as being this representation of what the programmer actually wants. Right? And so from there, we have a decoder, which is a neural network that goes and spits out a sketch of a program. Yeah?
I had a question on the previous slide. So
yeah.
The probability, I guess it's the same, but the probability like of y given x. So x is the keywords and so on, but this is like, the sketch itself is hard-coded in a sense, right? You have the abstraction from the scope of the sketch. So I don't know if it's generative in a sense because you take the keywords and you match to the sketch, but
no, you don't match though, right? So you're not, so you don't have an exact match of the keywords in the corpus.
Yeah, there's a definition, but like I was thinking whether you can actually learn the mapping as well.
Yeah, so learning the level of abstraction, so what that abstraction function is, I think that's a very interesting question. We haven't done that yet. So at this point, basically, think of it as the sketches as forming a higher level language, and we are just learning at the level of that language. But yes, what you ask is a very good question.
Just put a loop around it.
Yeah, that's possible, but it would raise some challenges, some technical challenges.
It's not just it. It's not easy, but
Yeah, sure thing. Okay, so I'm not going to go into the details of the model, but it turns out that the objective that I started out with, this maximal conditional likelihood, that can be approximated by this continuous function, the smooth function. And so training this neural architecture turns out to be a standard optimization problem that you can solve with gradient descent. Okay, so I'm going to talk though a little bit about the concretization method. So once you have a sketch, how do you go from the sketch to a program? So this is, as I said, this is based on traditional PL approaches. But just to say what that means, so think of you're starting with a sketch, and now you want to generate a program in your concrete language. So you have the grammar of your concrete language, right? So you can think of a generative process which starts with no code, right? And at each point fires one of the rules of your concrete grammar, right? And while doing so, it makes sure of two things. So first, that whatever you're firing, it matches the structure of the sketch that you have. And number two, if you get into some intermediate state, right, where you have some partial code, which is not type safe, and that's the beauty of type systems, that you can assign types even to incomplete programs. Then you can just throw that out, and that also leads to some pruning. And it turns out that the decoder that I didn't talk about also has a very similar structure, except there, this generative process is being carried out by a neural network. And I can tell you more if interested. So this is really what it is, right? So the two takeaways are that, number one, learn at a higher level of abstraction. This is good. This enables better learning. And number two is that going from that higher level of abstraction to programs use all of these PL ideas that we have developed over the last many years. And there's a lot that you can do over there. So here are some basic experimental results. There's more in the paper. What these numbers say is that you're looking at a test set, and you are talking about when the program that you generated matches the expected program in the test set, in what fraction of times. And we are only talking about the top 10 results here, right? So when did the expected result come in the top 10? And what we find, so these are, not to go into the details of the models, but whenever it says sketch, it means we are using a sketch. And whenever it says no sketch, it means we are not using a sketch. And so what we find is that over here, the bold values are the better ones. So the use of a sketch tends to significantly improve the quality of results. So here, for example, you see 59% accuracy for when the sketch is used, only 7% accuracy when the sketch is not used. And probably I should have compressed the table a little bit, but again, if you have questions, I can talk to you later about this. And what this picture over here shows that this encoding that we did over here, it turns out that it does it actually separate out programs according to their intent? Because I said that think of the encoder as basically generating the hidden intent of the program. So this is of course a very high dimensional thing, this encoding. But when you project it to a couple of dimensions, then you do see you can visualize clusters forming. So basically this is a two-dimensional representation of the encoding. And whenever I have a bunch of dots of the same color, that means that these are in the same API. These are points that use the same API. And so what we see over here is that programs that use the same API, they tend to be clustered together. And what that suggests is that this encoder is actually able to separate out programs into categories and specifications into categories based on what sort of APIs they're using. Yeah.
So how does your accuracy scale with the size of the sketch you're going for? So intuitively, I would think that as your sketch gets bigger and bigger, the accuracy should.
Yeah, it shrinks, right? Because there are more ways of getting things wrong.
Many more ways of,
Yeah.
you could just get it wrong.
Yeah, we did some experiments on that. I don't think it's the current version of the paper, but maybe we can talk offline. Okay, yeah.
I may have missed it. With that corpus that you're using there, where do you get the informal specification?
Right, so for this work, we basically took keywords that appear in the text of the program, and then did some splitting based on camel case and other kinds of heuristics, and then that's what gave us the X. But in principle, you could imagine, and we are actually doing that right now, Java comments as the natural language specification, and then you have the corresponding code.
So when I gave a Google talk on the AnyCode, which tries to do something similar for smaller expressions, some people from Google asked me, how is this better than just code search? So how is your thing better?
Yeah, so this is actually a very good question. So as it happens, over the last couple of months, I've been at Facebook helping out their code search team to implement something related to this. So the big difference is that if you're searching for a piece of code, you may find a program that matches your specification, but then you'll also get a bunch of other, it includes also a lot of other code that is very specific to the context in which that code was developed. So if you think of file reading, right? So you are going to get some API calls that tell you, how to open a file and read a file. But there's also going to be a lot of other code, right? That has nothing to do with what you want, but it's going to talk about, that specific application from where the code comes from. So the appeal of a generative model is that it lets you sort of average out over many different programs and filter out all of these very context-specific instructions, right? So you really get idiomatic results. So that's point number one. Point number two is that you have this probability distribution over sketches, which is actually coming from data, which helps you rank results. So if you think of, again, Google search, the ranking of the results is supremely important, right? But if you were just doing code search, you would have to rely on some ad hoc heuristics for doing that, which beyond a point, I think, are hard to scale.
So your matching process is essentially syntactic rather than semantic, right? So, like, you find a piece of code, right? How do you know what hidden assumptions are behind that code? Like, somebody's doing zero-based indexing versus one-based indexing, or their column row instead of row column. These kinds of hidden assumptions that really make it difficult to reuse code. How do you?
Yeah, this is an extremely good question. So, right, so we were just starting out here, and so we started with this purely syntactic notion of specification, but I think a natural next step is to add more semantics. So we are looking at two different ways of doing that. So one way is to basically add more semantic information in the abstraction language itself. So you can imagine having some predicates that capture various aspects of a program semantics and making that part of the way you abstract a method, right? So then when you are learning, you're learning over those abstractions of the semantics. But part two is that you could imagine also working with more formal specifications. So this idea of generalizing the specification, it's not going to necessarily make sense. So, but what would make sense is this idea of learning to search, right? So here, in some sense, you're learning to search because this generative model, the synthesizer that is ultimately concretizing the sketch, right? It's guided by the probabilistic model. So what that means is that it doesn't just go and look at all possibilities, right? It prioritizes some over the others. But you can take this much further. So if you have data about, here's a formal spec, what kinds of strategies are likely to work to meet this formal spec, that's something we could imagine doing.
Is it possible to train the whole thing end to end? Did you consider making the synthesizer differentiable or using something like reinforced?
So that's an interesting question. I'm a bit skeptical, but we are looking into that. Yeah. Okay. Yeah.
Have you considered using interaction to help with the fine tuning of the narrowing down?
That's a very interesting question.
Mm-hmm. Just doing the probabilistic, because probabilistic is of course
sure.
biased towards
one,
but maybe the user might see something more
sure.
useful or intricate in the choices.
Yeah. So in principle, it can be cast into this probabilistic framework, right? So you can think of getting back some results, and then you have the user providing some additional information. You condition on that information, and you get a new probability distribution, and so on and so forth, right? So it's possible. There are some technical difficulties, but we are also very interested in that problem.
Are you working on something similar?
Yeah, so we are looking at specifically this problem of, you have so let's say that you get a bunch of results from this. Now the user gives an additional constraint, right? So let's say that I don't want programs with print statements, right? So that's a constraint, and then you can imagine, having a conditional distribution that basically says, okay, you have your older distribution, now condition it further on this additional constraint that comes from the user. Okay, and now give me some samples from the resulting distribution. And this process could keep on going, right? You could get more and more and more constraints. But yeah, so there are some challenges over here, but again, we can talk about it offline.
So perhaps to sort of vary on the last couple of questions.
Uh-huh.
This reminds me now of something I saw a few years ago. I can't remember where, maybe at Ipswich or something.
Mm-hmm.
It was code completion based on execution context.
Mm-hmm.
So I think you could have a program that maybe had a hole or an incomplete bit of code,
Mm-hmm.
and when you got to that part of the execution, you could then hit dot, and it would supply all the methods that might be relevant in that execution context. So I guess here you could kind of imagine that you could give an informal specification that would be, I want something that computes this particular string,
Sure.
given this data that's in this context. And
Sure.
maybe the question that was asked earlier about, whether it's zero-based or one-based array indexing, for example, you could kind of consider the different executions of all the code examples that you pull back and kind of weight them according to whether they produce the right.
Sure, that makes a lot of sense. Yeah. Okay, no other questions? If not, I'm going to, let's see how much time I have. Okay, I have a little bit of, 5 minutes? Okay, so then, let me do one thing. Let me just skip the next part, and I'm actually going to go to the third application about which I didn't really talk. I didn't really plan to talk much about that, but this may be of interest to you. So this is a very different setting. This is program synthesis in the context of traditional machine learning problems such as perception. And so what do I mean by that? So imagine that you are doing this sort of synthesis from input-output examples, but your inputs and outputs are these fuzzy objects like images and so on. So what do you want? Well, you want to do the standard kind of supervised learning. So in supervised learning, you have inputs and you have outputs, and you want to find a function that fits this. But here, we are not going to want a function. We are going to want a program in a higher level language. Now, why would I want that? So I'm going to clarify that in a second. But before I do that, let me just tell you about one concrete example of this. So imagine that you're a baby, you are learning to count toys, and your input-output examples are something like this. So there's a picture containing a bunch of toys, and then the output, the answer that you are expected to give is how many toys of a certain kind are there. Okay? And we want to learn a program. We want to synthesize the baby. We want to learn a program that is able to perform this task. Okay, so why do we care about programs over here? So the reason lies in this challenge that has been very important in machine learning in the recent past. And this is that of transfer. So if you have a baby who's learning to count toys, if you ask the baby to count butterflies, he or she is usually able to do that, right? So there is some transfer of abstract skills that happens from one counting context to another. But if you think of a deep neural net, you are really going to have to train it 2 different times if you're just following the standard deep learning methodology, right? So once for this data set of counting toys, another one for the data set for counting butterflies. So the appeal of programs is that the biggest feature of programming languages is what? It's compositionality, right? So if you think of transfer, it's really very closely related to compositionality. So if you had, instead of this monolithic neural net, you had this compositional program, this modular program that represented a task, you could imagine taking a module out of that, namely the module for deciding whether an object is a butterfly or a toy, and you could switch it out in a different context, and then you would have a different kind of counting algorithm. That's kind of the high-level intuition. Okay, so then let me make this a little bit more concrete, and this is where I'm going to get into functional programming. So how would a functional programmer write this function of counting, taking, let's say, a list of images and counting the number of a certain kind of object, let's say a digit D. So what they would do is that they would take they would write a function called, recognize D, recognize the digit D, and then you would map over the list, right? And then you are going to fold over the list, and you're going to, that's how you're going to get the count of, all the elements for which this recognized D is evaluates to, let's say, 1, right? So it can evaluate to 1 or 0, let's say. So now, if you want to transfer this to a different context, you would just replace this recognized D by recognized T, right? So you're going to have a different kind of recognizer, but then the overall structure of the program would stay exactly the same. So now in our context, so this recognition is fundamentally a visual task. So you are taking a picture and you are deciding whether it's a digit or a toy. And so this is something that we implement using a neural network. So we basically have this programming language where you have these library modules, which are these neural nets, and then you have all of these higher order symbolic combinators on top of that, right? So it's like a Haskell with neural modules. Okay, so how do we go from here to a program that counts toys? Well, as I said, I'm just gonna switch recognize D by some toy recognition. So what's the advantage of doing this? Well, it turns out that there is this beautiful connection between neural nets and functional programming, which has been known for a long time, but it was elaborated in this blog post from a couple years back. So all of these standard neural architectures, they can be represented very nicely using these symbolic combinators. So for example, what's the most basic operation in deep learning? It's function composition. Composition of layers is really composition of functions. And the way these higher order combinators like fold and map and so on come in is that when you have architectures like recurrent nets or convolutional nets, you can think of them as operating over data structures in this very structured way, right? Which can be captured in using combinators. So for example, an RNN, which just reads a sequence from left to right and accumulates a value, that you can very naturally describe using a fold. So what this means is that a lot of these classic neural architectures you can represent using these little functional programs, right? Where of course you have these elementary blocks which are neural modules, which is what we have in the language that I showed you. So the other beautiful thing about functional programming, or this kind of combinator-based functional programming, is that they're very friendly to synthesis. So this is actually something that we have looked at in the recent past from a few years ago, where we had, our goal was to synthesize these complex data transformations. And then we came up with a little language of functional combinators in which these data transformations had very, very compact representations and allowed, therefore, more easy search. And it turns out that the type systems that the types that you get in such languages, they also allow you to do a lot of pruning, like throwing out programs that are not useful. So now if you put the two together, then you have this immediate idea that, hey, functional programs are easier to search over. Functional programs naturally represent neural architectures. Why not use functional program synthesis to do architecture search? And that's what we do, right? So it turns out that this idea allows you to search through vast spaces of architectures really, really fast. And these architectures also include, these kinds of modules, library modules, right, which are neural networks. And then you can, generate programs like the ones I showed you in a relatively small amount of time. Yeah, so this work, I'm not going to go into the details of the language. Basically it's a higher order functional language where tensors are your basic data type, and we have a little refinement type system where tensor dimensions are they are part of the type. And then there is a type inference algorithm that works on top of this. And we have some pretty interesting results. So this is joint work with Charles Sutton's group. And if you are curious, just look at the experimental results in the paper. So we have these sequences of tasks, and we show that there is transfer of knowledge from one task to another. So counting toys to counting digits and other things like that. And so I'll now conclude. So I would say I have two main points. So number one is that program synthesis has a lot to offer mainstream AI tasks. You have many advantages when you're representing learning models using higher level programming languages rather than using something like neural nets. These higher level languages lead to more interpretability. They allow symbolic verification. This is something I was going to talk about in the second part of the talk, which I didn't actually get to. And also things like composition, right? Composability. And the other part of this is that program synthesis needs machine learning. This is something I talked about in the first part of the talk, that ambiguity is a fundamental thing that we in the formal methods community have traditionally just wished away, but it can't be wished away. We have to deal with it, and machine learning is really a big part of it. And learning can also help us scale search, right? That's something that also has not been explored too much in this world. And with that, I'll end. Thank you very much. Yeah?
So I just had one comment on the second part. There was this paper on that was doing differentiable architecture stuff for convolutional networks. Did you look at this?
I know of that work, but we couldn't compare with that. It's these architecture search papers to do the architecture search, you need a huge amount of compute, and the code is often not available. So, but
it's just that it's differentiable, I guess. You're also differentiable, right?
So our end products are differentiable, but the method that we are using to search over architectures is program synthesis, right? So that's more discrete. Yeah.
Thanks.
Sure.
Yeah, I was trying to get time, but very, very quick question I was confused about in the last part. Is the training happening? Is it just doing search or?
Yeah, it's training. So okay, so that's a slide I sort of skipped. So the methodology is that you synthesize the high-level structure of the neural network using program synthesis. Okay, so you basically generate a type-safe composition of these basic pieces. But then this result is still parameterized, and there is a data set that you have to train it on. So it's a two-phase thing. So there is synthesize, and then you train.
But what is the signal for the first phase? Like, why would it come up with anything useful in the first phase?
So the signal is that the data is annotated with types. And so this type allows you to rule out, so for example, you want to go from images that are 32 by 32 by 32 to something else, right? To some data type. And so this type information is something that is leveraged in the search for the architecture. Because that means since this is the end type you're looking for, so your intermediate types also have some specifications on them. Yeah, so at this point it's more like type-directed search, but then you could imagine other things as well, bringing in the signal from the training into the search process.
Is that to enable parameterization? Because that's what I'm hearing when you're saying you're kind of going to be able to use the same thing and parameterize it, so you can use it for different examples.
Yeah. Because so the parameters do not decide the end input and output types, right? So you have so I guess that's an insight that if you have a neural net, right, you can assign a type to it that doesn't depend on the values of the parameters. So, yeah.
A question in regard to the first part. So you introduce abstract language for search, then you do the synthesis. So I'm wondering if it's a language of abstract text, the language model based on that will increase the entropy or lower entropy for the predictability.
Yeah, so this is related to the question you asked earlier, right? The regularity in the lower level and the higher level. So I think that's an open question. I don't know the answer to that.
So there's no empirical data to say what's the entropy for the.
We didn't measure that, no. Yeah, but I think that's an interesting question.
Yes, with respect to program synthesis, the thought I had when I looked at your example is that if you have enough examples of a pattern as for a deep learning approach to learn it,
Mhm.
the models are pretty complex.
Mhm.
The idea is that this pattern sounds like it should be common enough as to be in a library, and that it needs to be kind of abstract from the domain, because if it's very
Yeah.
domain specific, it will appear only like once or twice.
Yeah.
So it's like, have you considered that? Like, how common are the patterns that you can synthesize? Because if they are often available in libraries,
Yeah.
or you can just write a library for them, it's like...
I totally agree. I think somebody needs to write a paper on, language evolution using these kinds of models, because you could imagine that, as you learn these patterns, you could, abstract them into a module, and then you could just go ever more abstract, right? And then maybe, that would lead to a beautiful language, but we don't have that yet.
Yes, but what I mean is like, did you measure whether you can synthesize programs that are not part of a library already, or that's what I mean?
Yeah, so, right. So we are working with a fixed API, right? A fixed set of APIs. So we are working with the whole Java namespace, but, so there are a lot of libraries over there. But the individual method calls that you're making and the types you're using, they all come from some library. So the compositions are not just part of, they are ways in which libraries are used, but I don't think that they're just part of some other library. Now, in principle, you could create such a library. That's what I was trying to say. That, you could imagine a method that kind of, yeah.
Okay, good.
Okay.
Maybe since coffee is waiting, let's thank
Okay,
Swarat.
sorry for going over time.